This is wastewater treatment certification training, Chapter 7, disinfection. Commonly used disinfectants for wastewater are chlorine compounds, like chlorine gas, hypochlorites or chlorine dioxide, UV light, ozone, and a newcomer, peracetic acid. Chlorine, calcium hypochlorite, and sodium hypochlorite are used at smaller facilities for disinfection of wastewater. Chlorine dioxide is favored because it does not react with ammonia to make chloramines, but chlorine gas is still widely used in larger systems. Chlorine disinfection, the primary function is disinfection of the effluent. You don't want to put pathogens out into the receiving streams. Chlorine can also be used to control odors and control filamentous bulking. The recommended minimum detention time is 30 minutes for the water once chlorine is added. When chlorine dissolves in water, a combination of hypochlorous acid and hypochlorite ions will be formed. These compounds are the agents of disinfection. Hypochlorous acid is a more effective disinfectant than hypochlorite ion. The relative concentrations of each is dependent on pH and to a lesser extent on temperature. Chlorine disinfection is most effective between a pH of 4 through about 7.5. Around 6.5 to 7 is where the disinfection is most efficient. You can see by looking at the graph, that's where the hypochloric acid, this is the hypochlorous acid on the bottom. This is the hypochlorite on top, or no, it's hypochlorous on top on this one. At lower pHs, you make more hypochlorous acid than you do hypochlorite ion. Breakpoint chlorination. All this is saying is you have to add enough chlorine to get past everything that's in the water before you can be sure you've done an effective job of disinfection. When you first start adding chlorine to water, it's immediately used up by inorganic compounds and reducing agents. As you keep adding it, you make some combined residual with chloramines and chloroorganics. You keep addition, you oxidize the combined residuals, the chloramines, because chlorine tears them apart. You go back to the bottom again, and then every free milligram per liter of chlorine you add will show up in your residual. The break point for secondary wastewater after treatment is approximately 25 to 150 milligrams per liter. Other uses for chlorine as a disinfectant. Chlorine is added at the beginning of the head of the contact chamber. Other uses include corrosion and odor control. You can use chlorination implant to reduce filamentous bulking, reduce digester foaming, reduce filter ponding and get rid of filter flies, and aid in sludge thickening. Your total residual chlorine, when you discharge your water from your plant, before it goes into the surface water stream, you can only have 0.011 milligrams per liter total residual chlorine on a monthly average, and have a daily max of 0.019 milligrams per liter. It's not much. That is set like that because the fry of fish cannot tolerate more than trace amounts of chlorine, about 0.01 milligrams per liter. Measuring chlorine, you can use the spectrophotometric DPD or electrode method. That's 4,500 CLG. The amperometric titration method is 4,500 CLD. The iodometric technique is method 4500 CLB. Hawk reagents and spectrophotometer are EPA acceptable for KPDES and MPDES monitoring. When you're using those methods, calibration curve must be established using multiple standards and a blank. The calibration curve must be verified with a blank and at least one high and one low standard each day. These standard checks must agree within plus or minus 10% of the original scale value. There's your calibration curve. So before you use that every day, you need to run the blank, one of the low samples and one of the high samples to make sure that curve is still accurate. Chlorine exposure. Chlorine is hazardous. Some of the effects of exposure: at 1 part per million, you get slight symptoms after several hours of exposure. 10 to 15 parts per million, it irritates your throat. 30 parts per million, it causes coughing. 40 to 60 ppm, it is dangerous in 30 minutes. The number you really need to worry about is the immediately detrimental to life and health number. That's that limit there. It's 10 parts per million by both CDC and NIOSH. It's fatal in a few breaths within 1,000. So you really don't want to be in it at 10%, or 10 parts per million, I'm sorry, 10 parts per million. For dechlorination, since fish fry cannot tolerate more than trace amounts of chlorine, the effluent has to be dechlorinated before discharge. Typical ways to dechlorinate it is with sulfur dioxide or sulfites. There's all various sulfites you can use. Sulfur dioxide is most commonly used dechlorination chemical. In theory, if you have 1 part of chlorine, you'll use 1 part of sulfur dioxide. But in reality, most plants, they use 2 parts of sulfur dioxide to 1 part of chlorine to make sure, depending on, of course, water temperature and pH, to be sure they have very little residual chlorine. Sulfur dioxide dose is based on the flow and the total residual chlorine and what kind of residual you're shooting for, which for most wastewater guys, it's 0. Dechlorination is almost instantaneously. Proper dosage requires monitoring of the total chlorine residual and adequate mixing at the point of application. If you overdose with SO2, large overdoses results in chemical wastage, and therefore you're wasting money. Excessive sulfur dioxide reduces DO going in your water and lowers the pH. The effect of a 0.5 milligram per liter overdose might result in a dissolved oxygen depletion of 0.2 milligrams per liter. It can also cause an apparent increase in BOD. Properties of sulfur dioxide: colorless gas, sharp, biting, pungent odor. It's neither flammable nor explosive. Forms sulfurous and sulfuric acid when dissolved in water. It decreases in solubility as the water temperature increases, which is kind of unusual, but it does. Its density is similar to chlorine, so it's a sinker. It's heavier than air. The lowest concentration detectable by smell is 3 to 5 parts per million, and its immediately dangerous to life and health value is 100 parts per million. You can disinfect with UV light. It's what the bank of lights looks like. The bulbs are in quartz sleeves that must be cleaned regularly. UV light spectrum, it's a shorter wavelength than visible light, has more energy. It's between 100 and 400 nanometers. The UV breaks bonds in DNA, so the cells cannot make proteins or ultimately reproduce. If they get enough, they will not be able to repair the damage, enough dosage of UV. The regions of UV light, UVA is long range or long wave, that's 320 to 400 nanometers. UVB, the middle waves, 290 to 320 nanometers. It's UVB that causes sunburns. UVC is short wave, 200 to 290 nanometers. UVC causes skin cancers and cataracts. UVC is considered germicidal at 254 nanometers. Most of the UVC the sun puts out is absorbed by the ozone layer. The effectiveness of UV disinfection, dependent on the lamp intensity, the lamp age, and how clean it is, and how clear your water is. Exposure time, what's the contact time? Water conditions, what's the turbidity, the iron, the hardness, insoluble organic materials. There are no residual disinfection, so any pathogens that may have survived or were introduced after the wastewater is passed by the light source will not be removed. But there's no need to add anything to take out anything either. Low pressure lamps, its total UV available is much less than medium pressure lamps. UV light from a low pressure lamp is monochromic, with approximately 85% of the UV radiation being produced at 253.7 nanometers, the germicidal zone. It's good for smaller facilities up to 0.5 million gallons a day. Medium pressure lamps, higher UV intensity, 8 to 16 times higher than the low pressure lamps, but it's less power efficient. It takes more electricity. Fewer lamps are needed, however, so that's another plus. The UV radiation is emitted over a broad spectrum of wavelengths, 200 to 580 nanometers, and there's more germicidal zones in that wavelength range. So it's more germicidal than the low pressure. Excuse me. Low pressure, high output. It's produced at higher intensity UV at lower pressure in the lamp. It's effective for most flow rates. And approximately 85% of the UV radiation is produced at 254 nanometers. There's low pressure, a medium pressure setup. That's probably low pressure, high output. That first set we saw at the beginning was low pressure. Lamp life, low pressure lamps, it's recommended you change them every year. So that to make sure you have enough energy going into the cells to destroy the DNA, you need to follow the manufacturer's recommendation. Medium pressure lights get changed a little more often. Always check with the manufacturer of the system that you're using. What would you think if you saw this system? You were at a wastewater plant and saw this. Do you think that's a good system? There's broken bulbs, the sleeves aren't changed. It looks like a couple of the lights don't even have sleeves on them. Why turbidity matters? Turbidity can cause UV light to scatter and shield a pathogen from the UV lamp intensity. So the DNA would not be damaged. The advantages of UV. UV is effective in deactivating viruses. bacterial and protozoal spores and cysts. UV is a physical property rather than a chemical property. It eliminates the need to produce, store, or transport hazardous, toxic, or corrosive materials. UV is user-friendlier to operators. Just remember, if you're looking at the bulbs and they're not underwater, make sure you've got eye protection on so you don't burn your eyes. They take shorter contact time, 20 to 30 seconds. Less space is needed for disinfection, and there's no residual to deactivate or remove. Disadvantages of UV disinfection: inactivation or viruses and spores may not occur at low dosages. Organisms can repair their DNA if the damage is minor. You must have a preventive maintenance program in place to clean the tubes. TSS levels must be below 30 milligrams per liter in your waste stream, your effluent stream, for effective disinfection. So you must have good secondary treatment of your wastewater. You can use ozone. Oxygen primarily exists as O2 molecules. Ozone is made up of 3 oxygen atoms, so it's O3. Ozone is created in nature by the combination of oxygen in the air and UV light or electrical discharges, like during a lightning storm. The weak bond holding ozone's 3rd oxygen atom is unstable, therefore it's highly reactive. It'll oxidize whatever it hits. It's a powerful oxidizer. Direct oxidation and destruction of the cell wall with the leakage of cellular constituents outside the cell. Ozone decomposition creates radical byproducts. It can cause damage to nucleic acid. And there's a line in the book that says it's 31 times faster than chlorine, but we can't find a reference for that. The dosage needed: dosages between 5 to 15 milligrams per liter are commonly cited for disinfection of secondary wastewater effluents. Contact time is short, a few seconds, but you have to have 30 minutes to allow the water to degas as the ozone falls apart. You mix it by either using diffused bubbles or mechanically agitate the water. Advantages of ozone: more effective than chlorine, has a shorter contact time, but it says in the regs it's recommended a 30-minute detention. That's to allow the ozone to break apart. There's no harmful residuals. Ozone decomposes rapidly. There's no regrowth of microorganisms except for those protected by the particulates. Ozone is generated on site. Fewer safety problems associated with shipping and handling of chlorine. Ozonation actually elevates the DO levels in the effluent, so it'll keep you from having low DO. Disadvantages: low dosages may not effectively inactivate some viruses, spores, or cysts. Ozone is very reactive and very corrosive. Typically, if you're using ozone in that part of your plant, everything must be made of stainless steel so it doesn't corrode. Ozonation is not economical for wastewater with high levels of TSS or BOD5. So you have to have good secondary treatment of your wastewater to use ozone. Ozone is extremely irritating and possibly toxic, so you have to prevent worker exposure. The IDLH for ozone is 5 parts per million. The cost of treatment is high in capital costs to build the system you need, and takes a lot of electricity to generate your ozone. The newcomer on the block, peracetic acid, PAA. It's a reaction between acetic acid and hydrogen peroxide. It's a clear, colorless organic liquid. It comes 5 to 15% solution. It's a very effective disinfectant against many indicator microbes. You might need higher doses for spores, viruses, and protozoa. It's more environmentally friendly than chlorine. There's nothing that has to be removed from the water after you add PAA. It reduces and eliminates disinfection byproducts. Successful PAA dosages range from 1.5 to 4 milligrams per liter. 10 to 15 minutes of contact time is needed for bacteria removal. 60 minutes is the time it takes to remove the coliphage viruses. Trace amounts of PAA and hydrogen peroxide reduce the biofilms in your effluent discharge pipe, so it'll keep your system clean as well. It's been proven effective in systems up to 250 million gallons per day peak flow. One of the other advantages of peracetic acid is when the supplier you order the peracetic acid from, for most small systems, they will supply the pump and skid setup that's needed. And then they'll come and service that every time they come to check on the PAA supply. So most of the systems in Kentucky that are using it really like it. And that's the end of disinfection. If you have any questions, you can email your question to envhelp@ky.gov or call 502-782-6189 with your question. They will be forwarded to one of the trainers, and one of us will get back with you